Hello.
Yes, sir.
Okay. So let us start the fourth part of microstrip antenna. This part is important for your prescribed course because it contains the transmission line model for microstrip antenna. So basically, we are going to discuss the transmission line model for microstrip antenna in this lecture. So let us start. In the last class, we saw what is a microstrip antenna. We defined what is a microstrip antenna, or we saw how a microstrip antenna is constructed. It contains a ground plane. Above the ground plane, there is a super substrate, and on the substrate there is a conducting patch, and conducting patch is fed. Either it is coaxially fed, we give a feed line, or we can give a microstrip line feeding to it. So here we are showing, I am showing you the total of microstrip antenna, which has a ground plane and a patch. In between them, a substrate is sandwiched, and to the patch there is a microstrip line feed. Now, if you look at this, in the last class also, I said that if I look at this, the upper patch and the ground plane both are conductor. So two conducting plates, there is a separation between two conducting plates, and that separation is filled by a dielectric. So that we can easily correlate to a capacitor. So this is something like a capacitor. If it is a capacitor, then it will be an energy storing device. So from this, there cannot be any radiation because energy will be stored. Minimum energy will go out. So it cannot radiate. It cannot radiate. Now let us see actually what happens here. Why it radiates? So I'll take a cross section of this. The picture that we are seeing, let us take a cross section of that picture. So if I take a cross section, you can see there is the ground plane at the bottom, which is chocolate color or copper color. There is in the top there is a patch, which is again chocolate color. So green arrow shows the patch. And the feed line also is connected on the left side, which is a microstrip line. The thickness of the substrate, that is the distance between the ground plane and patch, that is called the thickness of the substrate, that is H. H is my thickness. The dielectric constant of the substrate is epsilon r, which is the relative dielectric constant. Length of the patch we are taking here as L, capital L. Now the substrate extends from the ground plane to the patch in the z direction. So there is a z direction that is shown. The patch is in the xy plane. The length of the patch is along x, width of the patch is along y, patch is along the xy plane. Then there is, you can see in the figure, there is an angle theta, which is with respect to the elevation or z axis. So there is an elevation angle theta that is not required in this slide, but it will be in a minute. I will say what is that theta or what is the importance of the theta, because if it is radiating, if it is an antenna, then in the far field, the field will be distributed in terms of angle theta and phi, azimuth angle and elevation angle. So this is theta, the elevation angle. Now we have two patches, so the upper patch and the lower patch. Therefore, and we are feeding that, since we are feeding that with AC, alternating current, or high frequency, alternating current of high frequency or microwave frequency. Therefore, there will be field which will extend from the patch to the ground or from the ground to the patch. So depending on the field distribution. Now what do you mean by field distribution? We are saying here, I have said in the last class, that at both the ends of the patch we have open circuits, which means there is current is 0, voltage is maximum at both the ends. So current is 0, voltage is maximum, then what happens? Voltage is maximum at both the ends, so it will not remain a maximum throughout the patch. What will happen is, so it will come up from the maxima, it will go to 0 at the center, then it will go to the minima. Therefore, the voltage maximum are of opposite phase. There is maxima, but they are of opposite phase. So if I take the amplitude of the voltage at both the ends, amplitudes will be same, but the fields at both the ends will be in opposite direction. That is what is shown in this figure, electric field. So you can see in the substrate, field lines are drawn, electric field lines are drawn. So these field lines are from the patch to the substrate, patch to the ground, and from the ground to the patch. So first left half it shows from the ground to the patch. So first half, so maximum at the patch, then it goes to 0, a maximum at the patch end, then it goes to 0 at the patch center, then it goes to the negative value of the maxima at the patch end. So that is how it is shown. Now look at both the ends of the patch. At both the ends of the patch, there will be some fringing field. Field will fringe out. Within the patch, you can see the field lines are straight lines. But as I go to the edge of the patch, the field lines are no more straight lines. They are fringing out. So there is some sort of curvature associated with the field lines, which are at the end. From the patch end, it comes to the ground plane, or from the ground plane, it comes to the patch. But near the patch, there is some sort of curvature associated with the field line. Now, why they are fringing out? I hope you have read capacitor. If you have read capacitor earlier, either in your pre-college or pre-university courses, when you have read capacitor, then you must have read on the Gaussian principles. At the end, if you use Gaussian principle, use a pillbox, that pillbox will show you that inside there is a line, outside you require a line. Inside the patch, if there is a line, outside you require a line, so that they will cancel each other. If they cancel each other, then within the box, total field will be 0. So that needs to happen. Because of that, there is fringing field. That comes from the Maxwell's equation. So I am not going into the fringing field description, how fringing field occurs, but we know, we have knowledge that at the end there will be fringing field. So here we are having some fringing fields. Now once there is fringing field, then we will try to understand what happens because of the fringing field. Now before going to that, let me again show you the top patch. In the top patch, what I have showed, or what I have told in the previous figure, is that patch is of width W, and that width extends along the Y direction. Patch is of length L, and that length extends in the X direction, and at X is equal to minus L by 2, we are having the feed line, which is a microstrip line. So we have a feed, we have a patch. The patch extends from minus L by 2 to L by 2. So total length is L. Along X direction, similarly, along Y direction, it extends from minus W by 2 to plus W by 2. So total width is W. And the origin also we can show at one of the ends of the patch. So that length will be W, length will be L, width will be W, G will be as it was. Now at both the edges, now just we have discussed, at both the edges of the patch, left edge and the right edge, at both these edges, there will be some fringing. So there will be, the fields will be fringing fields. So now you see that on the left edge, the fringing field goes from the ground to the patch. So it is going in the upward direction, but since it is at the edge, there is a curve. So it is curvy. There is a curved nature. Similarly, at the right edge, it comes from the top to the ground, from the patch to the ground, and near the patch there is a curve. So it is curvy. Now, since it is curvy and we know electric field is a vector quantity, this curve we can resolve it into two components. One will be horizontal, one will be vertical. For the left one, you can see the left one and right one, you can see the vertical will be for the left one, it will be in the upward direction. For the right one, it will be in the downward direction. So they are in completely opposite phase, in the opposite direction. So if there is radiation because of these two components of the field, which is upward direction, on the left hand it is upward direction, right hand it is downward direction, they will cancel out that. So effectively that will be like a field which exists or which is bounded between the patch or within the substrate. It is not coming out of the substrate. It cannot come out of the substrate. And then you can see that in both the cases, there is the horizontal component is from left to right. So there is a component which is from left to right on the left edge. There is a field component. Similarly, there is a field component which is from left to right on the right edge. So at both the edges, which is both the physical edges are separated by the length L. So at x is equal to L by 2, there is a field which is existing or which is which exists from L by 2 to right hand side in the horizontal direction. Similarly, at x is equal to minus L by 2, there exists a field which is coming from left hand side towards minus L by 2. So that you can see in this picture. The next picture, so we can draw those field lines, those fields we can draw, which shows that at the edge we have basically electric fields which are going out or coming into the edge. On the left it is coming in, on the right it is going out. Now this field, this extension will be very small, not very large. It will be very small because electric field strength will die down as you go away from the charge. The plate is distributed with charges, so as you go away from charge, it will die away following Coulomb's law. So the strength will die down as I go away from the physical end, but there will be sufficient strength near the physical end. So we can say that physical end or physical edge ends at L is equal to L by 2, but then it extends. Actually the field is not going to 0, or current is not going to 0, or voltage is not maximum exactly at that point. It extends beyond that by an amount of delta. So we have that if there is a field existing at the edge, beyond the edge, then field will exist within either within a slot. There has to be two edges within which the field will exist. So therefore we can imagine that at the edge there is a slot. So there are two slots at both these edges. There will be two slots. Okay. So we have a slot 1, then we have a slot 2. So there are two slots within which the electric field exists, and that electric field comes because of the fringing nature. So two slots within which there is electric field. So if this slot is excited with an electric field, any slot excited with an electric field, that we can say that that slot is going to radiate. So that will be radiating. That from that slot there will be radiation. How the radiation will occur, that you know from equivalence principle that we have studied. For the slot or aperture, slot is equivalent to an aperture. So from that aperture there will be a magnetic current. So if there is electric field, there will be magnetic current. If there is magnetic field, there will be electric current. So here we have electric field, accordingly there will be magnetic current. Now as I told you, this slot will have a width of W because that extends along the width of the patch, and it will have a length delta L. We'll find out what is delta L, or we'll see an expression, empirical expression for delta L later. But the slot extension or slot width is delta L and slot length is W. Now this slot is excited with a field. There is a field, electric field existing within the slot. Therefore, there will be an equivalent magnetic current MS. S stands for the slot. So there will be an magnetic current. So each slot is excited by a magnetic current MS. So we have now two current sources MS which are separated by a distance L. So if you have two sources which are separated by a distance L, then you know that forms an array. So we have an array of two elements, two magnetic current elements separated by distance L. Now let us find out what is MS, or what will be the value of MS, the expression for MS. In the last class we discussed about the field within the patch. The field will be of the form, as I told you, in the mnth mode, the field will be of the form EMN, mnth mode. So electric field in mnth mode, that will be of the form E0, that is the amplitude. Then the variation will be cos m pi L by upon capital L, cos n pi W upon capital W. That is the variation in the mnth mode. But the dominant mode is the 1-0 mode. We have one half wavelength variation along the length L or in the x direction, and no variation in the y direction. So therefore, in the dominant mode, the electric field will be E10. So E10 will be put m is equal to 1, n is equal to 0. So cos 0 is 1. So therefore E10 will be E0 into cos pi L by capital L. Okay. Now if I put L is equal to 0, when I am on the left edge, L is equal to 0, cos 0. So therefore within the aperture E10 will be E0. Similarly on the right hand side, small l is equal to capital L. So therefore on the right hand side, again cos pi, that will be minus E0, but minus, we have seen the components are in the same direction, that again will be E0. So in the aperture, both these apertures or both these slots, the electric field will be EA, which is equal to E0. So aperture field is EA, that is equal to E0, amplitude of E, that is equal to E0. Now once I know EA, then we can calculate what is MS. So MS will be 2 times EA cross n cap. Now from where this 2 comes? EA cross n cap, that you understand from equivalence principle, I can get EA cross n cap. What is n cap? N cap here is Z cap. It is the normal to this slot. So slot aperture is in the XY plane, normal to it will be in the Z plane. So therefore n cap will be Z cap, G cap. So forget about, so that you understand. Now from where the term 2 comes? As I told you, as we discussed, we have the patch. Below that is the substrate, below that there is a ground plane. So since there is a patch above on the side of the patch we have got magnetic source, which means we have got 2 magnetic currents above a ground. Because there is a ground, there will be an image below the ground. So MS will have an image below the ground which is equal to MS, and when we take into account the image contribution due to the image, there are 2 MS, one is real, one is the image, and therefore you add them, that gives you 2 MS. From that that gives you 2 EA. So from that we get MS is equal to 2 EA cross n cap. So that will be my MS. Once I know what is MS, then I can find out what is my field distribution, because I know current. Then once I know the current, magnetic current or electric current, here we know magnetic current. So once we know magnetic current, then we can find out the we can use the vector potential principle, as you know. From that we can find out electric field. So if for this, if I find out the electric field, the expression for electric field will be, theta component will be E theta is equal to E0 cos phi F theta phi. F is the field component. That we'll see. F comes from this ms. Then E theta is that. E phi will be, expression for E phi will be, I phi will be minus E0 cos theta sin phi F theta phi. Now what will be F theta phi? F theta phi will be this. F theta phi is equal to sin kW upon 2 sin theta sin phi divided by and kW upon 2 sin theta sin phi into cos kW upon 2 sin theta cos phi. Now this cos theta, cos kW by 2 sin theta cos phi, that comes because of array. We have a 2 element array. If you have 2 element array, then for the 2 element array, and the pattern is the array factor is of the nature cosine cos phi or cos theta. So here we have got that form, cosine kW upon 2 sin theta cos phi. But the first part is the element pattern, that is the radiation pattern or radiation field due to ms, which is equal to 2a cross n cap or E0. So from that we get this. Now here there will be an E0 term. I can take E0 to be 1. If E0 is anything else, then multiply that with the theta pattern. So that is what we can do. Now we have found out what is E theta and E phi for the patch. Now once we know what is E theta and E phi, then we can find out the principal patterns in the principal plane, E plane and H plane. For the E plane, this will be of the form F E theta will be of the form cosine kW by 2 sin theta, because in the E plane we have phi is equal to 0, put phi is equal to 0, cos phi will be 1. So cos phi is equal to 1, so that value you get there. Also F E theta becomes that. Then in the is it visible? Is the slide visible?
Yes, sir.
Yes, sir.
Okay. And then for the H plane, and phi is equal to 90 degree. So put phi is equal to 90 degree and you will get Fh is equal to cos theta sin kW by 2 sin theta upon kW by 2 sin theta. So these are the two radiation pattern or radiation fields in the two principal planes. So this is all about the fringing field and the effect of fringing field. So what is the effect of fringing field that we have seen now? That we can model the patch antenna as two slots separated by a distance L and the fields in the slots are known. So if I take that, and then I can go for the modeling. Now in this part, last class I told you I wanted to show you how we feed the patch, because there were some questions. So let me try and to show you how practically, if you design a patch, how you are going to feed it. Last class I told you use a coaxial cable or coaxial feeding. The coaxial feeding usually in the patch antenna, the frequency range in which we use it, which is from 900 megahertz to about 5 gigahertz. In that range we use a connector, coaxial connector, which is called the SMA connector. You can see for the feeding, I have taken all these figures from the Google image. Now see, you can see the SMA connector. So this is the SMA connector. You can see there is a coaxial connector, which is the tip of the connector, and within the tip, which is the golden color, pointing out is the tip. Around that, there is a dielectric material, and the dielectric material goes into the outer connector, outer part of the connector. Connector has three parts. One is the outer part, which is shown in the as the flange or flange, or the portion connected to the flange on the back side, that you can see that there is a grooves on the back side. So that portion is the outer connector. So then we have a coaxial line, which is the central conductor, which is the tip, that you can see this tip. Tip extends from this point up to the bottom of the connector, total length. Then between this central connector and the outer connector, there will be a dielectric material. When we connect it to the antenna, what we do is, this dielectric material or the white portion, that we cut away. So that we will cut and throw away. So we are left with only the central connector. Then depending on the thickness of the substrate and the dielectric substrate, ground plane and the patch height, all those will take care of that. So that much distance of the central connector will be kept. Other portion will be cut away, so that when we put it from the bottom to top, then the top portion will be connected. Now if I are going to feed it from the side, you can see this on the left hand side, you can see practically designed antenna. Same connector is connected from the side one. So from the side, if I am going to feed it, so this will be like this. Then you can retain a longer path so that it connects to the patch. So you can see the patch here and connection here. Another view for another patch antenna is here. The patch is above. Below there is a ground plane, a partial ground. This is called the partial ground. Below one, upper one is the patch. Now the connector is connected. The tip or the thing which is protruding out, central connector, that is connected to the patch in the top, and in the bottom we connect or we solder the other part, the flange part, to the copper part. Now once this is done, then we connect it to a source. Now what is required? Actually, if I connect the connector, only connect the connector and leave it, then there is no energy coming to the patch. Or if the patch is in the receiving mode, then after receiving, the energy will not go anywhere, because connector is not connected to any circuit. Connector, backside of the connector is not connected to any circuit or any source. So if I am in the transmitting mode, from the source the energy has to come to the patch, or if in the receiving mode, from the patch the energy received energy in the patch has to go to the circuit. So that is why we require a coaxial cable. The coaxial cable will be connected to this conductor. Now you can see that here. This figure shows you the source, which is a vector network analyzer, that is connected to from that source. You can see the black portion, that is the coaxial cable that you are using when you are using your oscilloscope. Similar coaxial cables you are using, but for microstrip antenna, these coaxial cables are different. These are very costly, but these are coaxial cables. Right? So coaxial cable is connected to the microstrip antenna. Inside shows you the connection of the microstrip antenna to the microstrip antenna. So this is a vector network analyzer with which we measure the power or the field received by the microstrip antenna or given to the microstrip antenna. So there will be two ports. From one port you will give energy, on the other port you will receive the energy, or in one port you can give energy and get back the energy, then you will get S11. If there are two ports, S11 and S22, S12, S21, those you can receive. Here, in this measurement, you can see what is the S11. So S11 will be something like this. If I am using the microstrip antenna, or experimental, we are doing this experiment. Maybe in your batch you can see this vector network analyzer. If we obtain this vector network analyzer, if we put the order and the department gets it. We are trying this for 2 years. Till now we have not got it. Hopefully in your batch can see a vector network analyzer once things are normal. So this is about feeding. Now let me come to the resonant frequency part that we discussed in the last class. Whether we can improve that resonant frequency, the resonant frequency that we saw, the expression, now we can improve that resonant frequency. How we can improve the resonant frequency? As we discussed, because of the fringing field, the electrical path length is no more L. L is physical length. Electrical length, there is an extension on both the ends. In each end there is an extension of delta L on both. So there is a total extension, right? Total extension is 2 delta L. Now that 2 delta L depends on two things, on the L and the permittivity. No, 2 delta L depends on the permittivity of the path, and L is as such, L is controlling the resonant frequency of the path. Since L is controlling the resonant frequency and delta L depends on the permittivity, therefore improved resonant frequency expression will be controlled by the length of the path and the substrate permittivity. Now approximately this will be the resonant frequency expression is in the dominant mode. We have seen this F10, which is the 10 mode, dominant mode. In the F10 mode, F10 is equal to C upon root over of epsilon r into 1 upon 2 L. This we saw in the last class. Now L is physical length. What I am saying here is we have to change this L, right? So if we are going to change this L, then we have to find out how we are going to change it. In the last class, I told you that in the dominant mode, this should be L is related to the resonant frequency through a relationship which is KL is equal to pi. So from that we obtained the resonant frequency, KL is equal to pi. Okay, so that implies that L is equal to pi upon K, which is equal to L is equal to pi upon K, that will be equal to lambda d by 2. What is lambda d? Lambda d is the wavelength within the dielectric, within the substrate, right? That is the wavelength. In free space it is lambda 0, within the dielectric it is lambda d. So L is equal to lambda by d by 2. Now that lambda d is related to lambda 0 free space wavelength by the relation lambda 0 by root over of epsilon r. So if I have a dielectric, if I have free space epsilon r is equal to 1, therefore lambda 0 by root over of epsilon 1, root over of 1, that is lambda 0. So in free space you get lambda 0. For other cases it will be smaller than lambda 0 as long as epsilon r is greater than 1. So L is equal to lambda 0 by 2 root over of epsilon r. So that again implies that a higher substrate permittivity allows for a smaller antenna, miniaturization, and lower bandwidth. Lower bandwidth we will discuss why lower bandwidth, that I will discuss later. So that is one thing that we have seen. Then as I discussed now, there is physical length L and there is electrical length, which is L plus 2 delta L because of the fringing extension of delta L on both the sides of the length. So if I take that into consideration, then we will improve the resonant frequency calculation because we are considering the electrical length. Electrical length gives you, once we consider that, we get something called the effective length. Effective length is electrical length. L is physical length, then L effective or LE is equal to L plus 2 delta L. That is the effective length. Now what is delta L? This is the expression for delta L. So delta L by H, delta L by H is equal to this expression, the expression given in the right hand side. There you can see there is a term epsilon REFF, which is effective dielectric constant. What is effective dielectric constant? I hope you have read this in microstrip line. But if you don't remember that, let me refresh that for you. The effective dielectric constant is when you are using a microstrip circuit, the electric field is within the patch and the ground plane, but as you come to the edge, it is extending beyond the patch. So it sees two dielectrics. Because of the curvy nature of the electric field, it sees two dielectric. One is the free space which is above the patch and the dielectric substrate which is below the patch. So two dielectrics. So for that we say that the effective dielectric constant, the effective or the what is the dielectric constant of those two dielectrics? There will be, this will have one value, the other one will have one value. So what will be the net value? Net value will stay between these two. So if it is one, free space is one, the substrate is epsilon r, therefore it will be in between these two. Epsilon r plus 1 by 2. It will be around that. And empirical expression has been found out, which gives you epsilon effective, epsilon r effective as epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 into 1 upon root over of 10 times h by w plus 1. So that is the expression for epsilon effective. It's a effective dielectric constant. Now using this delta L to find out LE, we can replace L by LE in the above expression and epsilon r by epsilon r effective. So that will give you a more accurate expression. So from that this epsilon r you can take as epsilon r effective in this expression. So that is a more accurate expression for resonant frequency. And if you are uncomfortable with this expression for delta L by H, finding the delta L value, you can use a good thumb rule, which is delta L is approximately 0.5 times H. 0.5 H. So this is a good thumb rule that we can always use. That will give you pretty good value for the dielectric for the resonant frequency. So once we know this resonant frequency, now let us come to the effect of fringing field. What happens because of the fringing field? Let me take 1 minute for this. Now, for fringing field, what we have seen up to now is the microstrip antenna. At both ends, there are two apertures in which there is electric field, and those fields are radiating. Therefore, the microstrip antenna can be thought of as an aperture antenna, and the fringing fields at both the ends, the fringing fields at the two edges or at both the ends, they add up to catch or cause the radiation. Because of that, we get radiation. So radiation comes because of the fringing fields. Now you can see the animation. If I do the animation of the patch antenna, you can see there is fringing field at both the ends, and because of the fringing field there is radiation. Radiation is coming out. Now at the other two ends along the length, there also will be fringing field. But those fringing fields will be oppositely directed, so they will be out of phase. So radiation for that, for these two edges, will be cancelling out. So there will be no radiation due to the edge along the length, but there will be radiation due to the edge along the W. These two edges from which radiation comes out are called the radiating edge of the microstrip antenna, and the two edges which do not contribute to radiation are called non-radiating edges of the microstrip antenna. And this is about fringing field. If you want to see the field configuration, how the field is configured, this shows you the field configuration. Now here also you can see the vectorial direction of the field. Patch is fed using a feed, coaxial feed, and you can see how the radiation is coming out. And these figures, the Smith chart shows you the plot of the impedance plot, whereas on the left hand side you see the S11 plot, which is the reflection coefficient plot for this antenna. We will consider that when we will consider the input impedance or radiation. This we will see in detail, but this one shows you that this has a very narrow bandwidth. So that is why I have put this. It shows that it has a narrow bandwidth. That is important. Okay, good. Next, this shows the radiation pattern. I have told you, or we have discussed what will be the radiation pattern in the E plane and H plane. This is showing you the E plane and H plane radiation pattern. We will have a discussion. The upper one shows you the 3D pattern, and lower one shows you the 2D pattern. But we will discuss this later in a minute in the next lecture, not in the this lecture, in the next lecture. Left hand actually shows you the E field pattern, right hand shows you the H field pattern here. Now let me come to the important aspect, which is the transmission line equivalent. As we saw that this patch antenna we can think of it as two slots which are separated by a distance of L. But these two slots are connected because this distance L is as the patch. So they are connected, electrically connected. Since they are electrically connected through a microstrip line, we can say that it is a transmission line with both ends having two apertures. So two apertures connected through a transmission line. So that is why this model is called a transmission line model. So we have the physical length L, which is separating the two apertures. So the two apertures are modeled to have conductivity and susceptibility. So conductivity on aperture 1 will be G1, susceptibility will be B1. On aperture 2 it will be G2, susceptibility will be B2. They are connected, two apertures are connected through a transmission line of length L, and on this transmission line, at any point on this transmission line, we are trying to find out what is the input impedance. But here you see there are two apertures. Since there are two apertures, there is electric field, not current, there is field. So since there is field, electric aperture, we have got Z and V. So Y1 is equal to G1 plus B1, Y2 will be equal to Z2 plus B2. These are two admittances. Right? Since there are two admittances, it is always easy to consider the admittance. Find out what is the input admittance, because that will be, if they are in series, here you can see they are in parallel, so we can add them. Admittances always add in parallel. Admittances parallel are added up, and series adding is for impedance. So we can go for simple addition. Algebraic addition will be easier. Therefore, we will consider Y in, find out Y in input admittance. Then we can invert that, because Z in is equal to 1 upon Y in. So first find out what is equivalent Y in, then we can find out what is Z in. Now for this transmission line, the characteristics impedance will be YC, characteristics admittance will be YC, characteristics impedance will be ZC. You know, for a microstrip transmission line, I refer to the Pozier book or any other book, even I refer to the Balanis book. There you can find out an expression for Z0, characteristics impedance. So use that expression for Z0 or ZC and invert that. That will give you YC. Now what will be Y in? Y in expression will be, as you know from transmission line theory, Y in will be Y0 into YL plus J Y0 tan KL divided by Y0 plus J YL tan KL. K is equal to 2 pi upon lambda. So that we know. So once this will be the expression for Y in. Now what is left? We are left with finding out what is G and B. That is the problem. Now as I told you, Y1 on the slot 1 or on the aperture 1, the admittance of the aperture will be found out as Y1, which is G1 plus JB1. Now what will be G1? You can find out G1 for a slot of width W and a thickness H, or so slot of length W and width H. Here that will be this G1 has been found out by Roger Harrington. You can see his book, Roger Harrington book, in which he has dealt with extensively with slot. From that we get the expression conductivity of the slot is this expression. So G1 is equal to W upon 120 lambda 0 whole into 1 minus 1 upon 24 into K0 H square. Okay, this is valid so long as H upon lambda 0 is less than 1 by 10. Similarly, there is an expression for B1, which is W upon 120 lambda 0. So in both the cases that part is constant, and then 1 minus that part is constant, then 0.636 log natural K0 H. This is also valid for h by lambda 0 less than 10. Similarly, we will find out what is y2. Y2 will be, since both the apertures are same in construction, therefore y2 will be equal to y1. G2 will be G1 and B2 will be equal to B1. Okay, so this we will get. Okay, go. Okay. Now we will find out what is y2 at the input position. Now, as you know, y2 we have found out at the edge. Now we are giving an input. Now, or we are finding out the input, the impedance. So that position, it will be translated, as you know, using transmission line model. I have shown you in the previous slide, y in expression for y in. That depends on L or length from the edge or from the impedance y in or y1 to where we are measuring it. Now assume that we are measuring at it at the other edge, the edge 1. So first slot. If I am considering first slot, y2 transform, this tilde shows you the transform. y2 transformed will be g2 tilde plus j beta b2 tilde, that will be equal to g1 minus jb1 in the resonance mode. Therefore y in will be y1 plus y2 tilde, which is equal to 2g1, or y1 plus y2 transformed. Y2 transformed is equal to g1 minus jb1. You can see it putting these values in the expression that I have given you. So that will give you y in is equal to y1 plus y2 tilde, which is 2g1. Once I know what is y in, I can find out what is z in. So my expression for z in is equal to, z in will be equal to r in. Why r in? Because there will be no imaginary part, only real part. Real part is resistive only nature. So y in will be, z in will be r in, which is 1 upon y in, which is equal to 1 by 2g1. Now this one, this z in, this formula, this does not take into account the mutual coupling effect between the two slots. There are two slots which are separated by a length L. So there can be mutual coupling between these two slots. So that is not used here. Now suppose I want to take effect of the mutual coupling. So if I want to take the effect of mutual coupling between the slots, then this expression will change. This will become r in is equal to 1 upon 2 g1 plus minus g1 2. Now when I will use plus sign, when I will use minus sign, that depends on what is the mode we are using. If I were using odd modes, we will go for plus sign. If we are using even modes, then we will go for minus sign. So if modes are even, minus sign, because it is symmetric. If modes are odd, it is plus sign in case of asymmetric. Now the expression for G12, which is the mutual coupling expression, is given as this: 1 upon V0 square. V0 square is the voltage in the slot, a real part of integration, surface integration, or the integration of the surface of the slot area into E1 cross H2 star dot ds. E1 is field radiated by slot 1, and H2, this is not H1, H2 is the H field radiated by slot 2, V0 is voltage across slot. Now you can ask me how we have, this is for G12, what is G1, what is B1, how you are finding out this? Same thing, same procedure. Instead of H2, just put H1 and use those expressions. That will give you the value for G1. Now there is an expression for this. You can find out this expression in the Balanis book. I am not going to expand on this. So once we know this, everything, and let me give you a problem, and I will give you 5 minutes. After that, we will start the next lecture. This problem is, let us neglect the mutual coupling effect and find what will be the input impedance of a rectangular microstrip antenna with width to height ratio, which is W by H, is equal to 6 and W is equal to lambda 0 by 2. So this is given, everything is given, just find out what will be the input impedance for this microstrip antenna. After that we'll go to the next lecture. So we'll stop here, take a break of 5 minutes, then we'll come back. Audio बंद करो. आयो भूख लग देखा होगा सोई पड़ लगी यूट्यूब रे जाइथिल तो हाँ दिया मु खाइदेले पुणी क्लास ने भी तमे गपिला को मु खाଇବା बंद कर दिया था तरकारीटा बढ़िया ହେଇଛି
हाँ तो पड़े पासी टिफिन रे तो जाए इच्छा होती खाई दे
अच्छा मुझे नहीं सुन
समझ